Okay, now let's talk about the covalent bond. So I have wrote a very cliched thing about covalent bond, and that is sharing is caring. So the covalent bond is very positive. They want to share their electrons. They do not want to accept or donate their electrons. They're more towards sharing electrons and fulfilling the octet configuration. So here I have used two elements, one just like the other one, which is the one we used in ionic compound example, that is chlorine, and the other one is hydrogen. So from breaking down the electronic configuration of both, we see that helium, it just needs one electron to have a stable s orbital, and chlorine, just like before, needs one electron to have a configuration just like that of argon. So what do they do is, it cannot just donate its electron, because then hydrogen won't be hydrogen itself, it would be a proton, because a hydrogen has one electron and one proton. So what do they do is, instead they share their outermost shell electrons. So this is how the sharing takes place. So these 7 electrons are present in pairs, and the one unpaired electron forms a covalent bond with another unpaired electron of hydrogen, and this is how sharing of the electron leads to the covalent bond formation. And from this example, it's also very easy to remember that in ionic bond we had seen that the ionic compounds are usually comprised of a metal and non-metal, but in this case, in case of the covalent bonds, what happens is usually the participating elements or atoms are always non-metal. Hydrogen is a non-metal, we know that, and chlorine is a non-metal as well. Okay, so how do we represent a covalent bond? We usually use a bar or a line to show the covalent bond, but it's not always like there will be only one electron sharing between the two participants. It can be 2 or more. So when the elements, they share one electron, it forms a single covalent bond. When they share 2 covalent bonds, like the oxygen that is present in the air is present in the O2 form, which is the most stable structure of the oxygen, and in this case the oxygen, the 2 oxygen atoms, they actually form a covalent, 2 covalent bonds between them. And in case of nitrogen, we know that nitrogen has a valency of 3, and 2 nitrogen would always use 3 covalent bonds to have a stable configuration, like the octet configuration of the inert gases. So this is all about the covalent bond. Okay, now let's talk about the classification of the covalent bonds. So let us take the example of 2 covalent compounds here. One is methane and the other one is ethene. So here we see from methane that a single carbon is attached to 4 hydrogen atoms with all the single covalent bonds. But here we see that in ethene, the 2 carbon are bonded by 2 covalent bonds, and on the other hand, they are bonded to the other 2 hydrogen atoms on either sides. So from these configurations, it is evident that based on the number of the bonds, there can be the different types of covalent bonds. And we know that if the single bond is not as strong as the double bonds, so the higher the bond order, the higher would be the energy in the bonds. And so what happens when these atoms have a single bond, and what happens when here we see there are double bonds? So let's just remember that the covalent bond is of 2 types, sigma and pi. So all the single covalent bonds, S for single, S for sigma, all the single covalent bonds are sigma covalent bonds, and if there is more than one bond, then there would be one sigma and the other bonds would be pi bonds. So we would now study this balloon structure of ethene to get to know more about the sigma and the pi structures. Okay, now let's get to know more about sigma and pi bonds. So here we see I have drawn the orbital shapes of the electrons present in bond formation. So when we see in ethene, we know that there were 2 bonds between the carbon atoms. Now we see that the p orbitals of the carbons have formed 2 sigma bonds with the 2 hydrogen on either sides, and one they have used to form bond with one another. And then there is another bond, which is the pi bond. So just for ease, I would quickly write down the structure on one side. So here we see that 2 hydrogen on either side. This is the p orbital of carbon, this is the s orbital of hydrogen, and likewise. And here 1 p orbital of the carbon atom has formed the sigma bond. Okay, so what is this? This is a pi bond, which the other p orbitals of the carbon atom is forming the pi bond. So one of them is sigma and the other is pi. So the sigma bond is actually end-to-end overlapping. So if I were to use my hands, then if these 2 hands are my p orbitals, then the sigma bond will be when they are doing end-to-end overlapping, one over the other on the ends. But the pi bonding is not end-to-end, rather it is lateral, that is sideways. So which I have shown here, that 2 pi orbitals are formed through the sideway overlapping of the p orbitals, and here in the sigma bond we see that there is always direct interaction or the end-to-end overlapping of the 2 orbitals. Here we see that one carbon atom has a sigma bond with another carbon. Here both the p orbitals have a very direct end-to-end reaction, interaction, that's why it's a sigma bond. And likewise here the carbon's p orbital has a direct end-to-end overlapping with the hydrogen's s orbital. So this is a sigma bond as well. But in this case, this is not a direct end-to-end overlap, rather it is a lateral overlap. The 2 p orbital of these 2 carbon are laterally overlapped with one another through a pi bond. So whenever there is 2 bond, 3 bond or multiple bonds, one of the bonds will always be a sigma bond, which will have a direct end-to-end interaction, and one bond just be sigma bond, and all other bonds would be covalent bond, pi covalent bond. Okay, now we would see another example using triple bonds. So in ethene we saw that between the 2 double bonds of the carbon, one is sigma and the other is pi. And just like that, we will show now the structure of ethine. Ethine, that means it has triple bonds. So these 2 carbon atom has triple bonds, and so just like before, every one bond between the atoms would be sigma bond, and the other 2 bonds here are pi bonds. So in case of multiple bonds, just one bond would be single bond or sigma bond, and all the other bonds would be pi bonds. And when to talk more about sigma and pi bonds, well, the pi bond is less stronger than the sigma bonds. The sigma bonds are always way more stronger than the pi bonds, and the sigma bonds can be possible in any orbital, let's say s orbital, p orbital, d orbital, and so on. But in order to have a pi bond, it must be present only in p, d, f, and so on, never in the s orbital. So this is all about sigma and pi bond. Okay, so now let's talk about the properties of covalent compounds. So we know that the strongest bond among all the different type of bond is ionic bond. So since it has a greater reaction force, so the ionic compounds are always solids. But in case of covalent bonds, the attraction is not as strong as ionic bonds. So most of the covalent compounds are usually in liquid or gaseous form. And obviously, so just like using our very common sense, we can say that since these are mostly liquid and gases, so their low melting and boiling points will be lower than that of the ionic points. So they have low liquid and low melting and boiling points. And when it comes to solubility, we have already been introduced with the terms polar. So since covalent compound doesn't give any kinds of ions or charges, so what happens is these are non-polar in nature, and just like how we saw that the ionic compounds sodium and chlorine, they give the chlorine and sodium ions when soluble in water, so that the oxygen's partial negative charge can absorb the sodium and the partial positive charge of the hydrogen can absorb the chlorine. But in this case, their solubility would always take place in a non-polar solvent, just like benzene or ether, which are not polar as well. The non-polar solutes, all the covalent compounds are non-polar, so they would always be solvent in non-polar solvents. Like water is polar, but oil, they are not polar. So what happens when you mix oil and water? The oil would always float at the top. So this is just like that, since oil is non-polar, so in oil kind of organic compounds like benzene and ether, these non-polar covalent compounds are soluble. Okay, and the molecular reactions for the liquid and the gaseous covalent compounds are usually slow, and since most of the covalent compounds are, like all of them are organic compounds, so they exhibit isomerism. Just quickly rewinding isomerism is that the chemicals which have the same chemical formula but have different molecular structure. So yeah, this is all about the properties of covalent compounds.